Hello, everybody. Uh, Welcome back. Apologies for not uploading recently. I had my own exams to do and I had to make sure that I got those squared off. But for those of you who are currently taking the class, this probably isn't going to be much help for you because your exam's already done. But for those of you who are in the future and watching this is still going to be up for you, and hopefully this will be at least somewhat helpful. So let's get into this lecture here. So we're going to talk about protein purification techniques and characterization. There's a lot of stuff in this lecture but I don't think all of it is necessary. I think you can get by without going through all 47 slides here. So I'll try and pick out what's important and what's not important. Um, we already talked about all these things with peptide bonds and the phi and psi angles. So I'm not going to go over that. If you want to look at that again, go back to my lecture 5 video. I talked about it a little bit more. But yeah, this whole idea that they're constrained, right? You can't really rotate them. Secondary structures, different types of structures. You got alpha helices, beta sheets, right? And those are something you should know for the exam. And yeah, so the other thing is that they can be I don't know if I really talked about this too much, but they can be amphipathic. They're not always amphipathic though, right? If something's amphipathic, you expect to see like polar on one side and non-polar, and then like same thing here, you expect to see polar on one side, non-polar on the other. But and these are the patterns you should be looking for. This is like commonly this is just like this is just alternating, right? This is just alternating. This is known as I plus 3/4. Okay. Every third/4th amino acid is a is an amino acid of the same type as the first one you started with. So we start with polar right here, right? The next third one, fourth one are both polar. Third one, fourth one are both polar, right? Stuff like that. The other thing to find here is that like if you have a transmembrane helix, a transmembrane or transmembrane sheet, beta sheet, right? Those are within the protein itself. Those are almost always entirely hydrophobic. So just be aware that that is a possibility. Yeah, different types of methods. NMR. You never really are tested on these, by the way, so I wouldn't really worry about this unless you have a new professor and they really emphasize it in class. But I personally never seen this on an exam, and I've seen 2 years worth of exams for this now at this point. Or sorry, well, I guess 2 years. I've seen 2 classes worth of exams, and they don't have any of these. How do we work with proteins in the lab? Yeah, I mean, again, don't really care. Yeah, so I guess the main thing I want to, I guess, kind of look at here is these. These are the main methods that we actually use to categorize and characterize proteins, and then the gel electrophoresis is very important for denaturing and disulfide bonds. This is actually very important because it helps you figure out how gels work and how do you understand gels and what they mean, right? But yeah, I would focus on these for sure, right? And then this down here. The rest of these are like not too important. I mean, extraction's a thing. You talk if you take Biochem 426, you'll do this, but I wouldn't be too bothered about this for the exam. Um, yeah. So different proteins have different amino acids, right? So when it says surface charges, we're talking about like how certain proteins have certain charges on the surface. Some of them might be more acidic, some might be more basic, some might be a mix of both. So just be aware of that. Not all proteins are the same, right? And this whole idea here, I think, is supposed to be talking about salting out. Um, it's basically just this idea where oversaturate a solution with salt, the protein will eventually precipitate out because the salt ions will actually associate with each other and not the protein. Um, Gosh. It's basically a probability thing, right? So if you look in this first image, right? You're salting in, which means you're just putting salt in, right? And the solubility of the protein is pretty high in this case, like right. So um, the idea is that like as you put the salt in, the proteins, it'll attach to the protein, right, and then um, it'll become attached to the protein. It basically makes the protein able to but then if you add enough salt, um, eventually the salt will start associating with each other, and you'll get something like this where the salt is associating with each other, right, and the protein is separate, and this actually results in a precipitation of the protein. So what it's talking about here is um as we increase the ionic strength, right, so the amount of ions added, the solubility is initially increased, and then it decreases drastically, right? So initially increases, gets to this max point, and then decreases drastically, right? Bro, it's killing me. What the heck? Ooh. Okay. So, like I said here, salt at which protein precipitates is different, right? So some proteins will um, dissolve, precipitate at much higher salt concentrations, and some will require much less. Um, Other than that, I don't think much else of this stuff is important. Dialysis is cool. Basically, you just remove salt using osmosis, right, or chemiosmosis, right? It's pretty cool. Um, but other than that, I don't think any of this is really that important. Just the main idea I want to convey here is that salting out is a technique used to purify and precipitate proteins. First, if you have a protein in a solution, right, you can't see the protein. It's pretty dang hard. So what you do is you basically saturate that solution with salt. If I had this here, right, and let's say I have my protein, right, I don't know, let me leave this thing here. If I put enough salt in, right, if I put like a couple pieces of salt in here, right, it's not going to do much, right? The protein is going to be pretty soluble, so I can't see it, right? But if I add a ton, right, a ton of salt, right, you should be able to see that now this protein is kind of is now more visible, right? Because of the fact that I've now put in enough salt, and the salt is now associating with itself and the water. Basically, the water is being absorbed by the salt, right? And so now instead we have this protein that is precipitated out, and that you can now characterize and do NMR on and stuff like that. Yeah. So this is an idea, interesting idea, and actually very important, right? Variable solubility at pH equals pi. Why is that? It's because the pi is the point. The pi, right, is when the charge is 0. The net charge on the protein is 0. Right? So there's no net charge on the protein, right? That doesn't mean that there's no charge at all. It just means that there's no net charge, right? So 0 net charge, right? What do I mean by that? I mean that, if a protein has a plus charge and a minus charge, right? Those two cancel out. The net is 0. If it has plus 2 minus 2, still 0. Plus 3 minus 3, still 0, right? If it has 0, still 0, right? Basically, if there's a net of 0, then the protein is probably not soluble, right? It's going to be, or very minimally soluble, if anything. This idea of ubiquitin may change charge surface residue. This is just an idea that, like, if you, like, for example, lysine can be acetylated, right? The acetyl group actually changes the lysines and arginine actually as well. So it actually does not have a positive charge anymore. So basically this idea is that attachments can change the charge of things. Another example is like phosphates on serines and threonines, right? It turns it from neutral to negative, right? Stuff like that. It's just an idea that modifications can change the charge of many proteins. But yeah, charge is a function of pH. This is the idea of like pKa's and pH, right? So if you have the pH, right? pH is a variable thing. So pH is variable, right? So this is a variable concept, right? It can be changed. So like pH can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, right? The pKa, on the other hand, is a constant for any given amino acid. So like for lysine, for example, it's around 10.7 pKa, right? If pH is above pKa, right? So if I had, for example, 12 pH, right? I'd be in the basic form of lysine. I'd be deprotonated. If I was below the pKa at around 8, right? I would be protonated, right? So in physiological conditions, right, at pH 7, lysine would be protonated, right? The same thing applies for pi. Pi is a constant value of the protein, pi, right? And all pi is when the net charge is equal to 0, right? But it's made up of the combination of a lot of these amino acids in the protein, right? It's basically the pKa of a protein, if you want to think of it like that. Okay. If we look here, right? Right, so the important thing here is to realize that the D and E are the only acidic amino acids, and then R, K, and H. So arginine, glycine, histidine versus aspartate and glutamate, right? If the number of acidic residues, so aspartate and glutamate, is higher than basic residues, then the pi is less than 7. right? That should make sense, right? If I have more acidic amino acids, then the point at which the charge is 0 should be more skewed towards these negatively charged amino acids, right? These acidic amino acids. On the other hand, right, like I said, acidic protein, right? On the other hand, if it's skewed in the opposite direction towards these, right, it's the opposite. It should be greater than 7, right? Basic proteins, right? And you can do the whole number line technique. I talked about this number line technique before, right? If you've worked with me in person, you've also seen me use it, right? The idea that if I have a number line, right, and I don't know, let's for example, let's say we have lysine, arginine. So lysine's around 10, arginine's 12. Let's do histidine 6, and let's do aspartate or something. I don't know. All right. So if my protein has this, technically there should be an N. So yeah, let's go and do the not do. And there should be an N and C terminus always in a protein. So if I go all the way down to 0 pH, right, at this end, right, what's the charge going to be? Well, I got lysine, which is plus, arginine, which is plus, N terminus is plus, so plus 3. Histidine would be plus, so it'd be plus 4. This aspartate or would be that's actually glutamate. Glutamate would be protonated, right? So it'd be neutral, and then this would also be protonated. So we'd be down at plus 4 down here, right? Then we'd move up here, plus 3, plus 2, plus 1, 0, and minus 1 and minus 2. So notice how the 0 point is between 9 and 10. So if you take the average of these points, right, so 9 plus 10 is 18, divided by 2 is 9. So the PI of this is going to be 9, right? Notice how, because we have more basic amino acids, a 12 here, right? We have a basic 12 here. We've got a 10, we've got a 9, we've got a 6, right? See, notice the 6 is not really too basic, but like it's basic enough, right? Notice how, because we've got more of these basic residues than acidics, right, our PI is now greater than 7, right? Right. So yeah, so like if you should be able to do this, right? So if the PI is 5, then at pH 7, what is it going to be? Well, if pH is above PI, right, then we're going to be negatively charged. We're going to be in the basic form. So it's probably going to be negative, right? And yeah, so if you look at this, right, so if the PS, this is really weird, actually. I don't know how I feel about this. I guess like they're trying to look at this protein, right? So yeah, if you look at fraction of solubility here, a horrible circle, but at this point where there's minimum solubility, right? That's the PI of this protein. So around 4.6 for this one here. It's around 8, right? And then at pH 5, right? A is much less soluble than B. So A is 5 is around here, right? That makes sense, right? Because protein A's PI is 4.6 and protein B's is at 8. So that makes sense, right? Because if it's closer to the PI, the more neutral the protein's going to be, right? So that's how that works. This is cool. I don't really care. I mean, this it's interesting that like different organisms have different like PIs and stuff like that for proteins, but they're not going to test you on this. Column chromatography is cool and interesting. We'll cover more of it later. Basically, it's just the idea that proteins separate based off how fast they flow out a column. But I don't think they've ever tested me on this, or ever tested anybody that I've worked with on this, so I'm going to move past it. Okay, this is the first real technique that you'll see on an exam, size exclusion chromatography. Okay, so the main idea with this is you have a tube, right, like this, right? And this tube has beads, as shown in this image here, right? And the interesting thing about these beads, right, is that these beads have little holes in them that allow small things to get stuck in them. That means is that the bigger things actually fall through the sides. So you see this yellow protein here, this yellow ball, the green ball here also flows through the side. So bigger things flow to the side, while smaller things get stuck. That's exhibited here, right? Tiny holes. Smaller proteins enter holes, right? While larger proteins enter through the sides, right? Yeah, so smaller proteins, right? I read this completely wrong. Yeah, smaller proteins, right, take longer to go through the resin, right? Makes sense because they get stuck in these beads here, right? In these little holes. Yeah, and proteins that do not enter the resin
like I said before, pass way quickly through the column and they elute first, right? So you expect larger proteins to elute first and smaller ones to get stuck, right? And that's shown here again, right? Yeah, so like for example, right, if I had this, right, this 3 to 70 kilodalton one, right, if nothing got stuck in these beads, I would say, okay, that means that the protein is greater than 3 to 70 kilodaltons or less than 3 kilodaltons, right? If it's less than 3 kilodaltons, it'll also go straight through. But like if it didn't get stuck in this, I would say, okay, it must be below 3 or above 70. If it did get stuck in this, I would say, okay, it must be between 3 and 70, right? Uh, yeah, I mean this is also true. I don't know how important the rest of this is, right? We already talked about this, right? The whole size, of course, this makes sense, right? Defines the size of the protein, right? If the whole is bigger, right, then you can the larger proteins will get stuck more often, right? And but yeah, there's different types of resin, right? But other than that, I don't think the rest of this is that important. Yeah, this is I don't think this is very important. Yeah, so for this, I already talked about this, right? So like for larger proteins, they'll go around the sides, like this green, yellow. That's all there is to that. I think the rest is really that important. Yeah, so this right here is kind of reiterating what I said, right? Proteins greater than 70 kilodaltons will come out together and they'll come out first. Same thing here. Anything below 3 also comes out together. But they'll come out last, right? Because they still get stuck, right? But they're not it's like they get so stuck that they kind of like don't actually go they basically get so stuck that it takes the bulk of the stuff is already left before they are actually able to come out. So I actually think I might have messed it up there, but keep that in mind, right? Larger stuff will elute first, then smaller stuff will elute last, and the smaller stuff gets stuck in the beads while the larger stuff does not, and that is shown here. Uh, yeah, so they measure absorbance. They measure absorbance at 280 because tryptophan and tyrosine are amino acids that actually absorb that wavelength. Yeah, so you can see here, so the void peak, right? This is probably where all the big stuff is, right? Because it is eluted out first, right? And this is the back, right? This is where all the small stuff has eluted out, right? And this is where the bulk of your actual protein has eluted out. Yeah. Ion exchange chromatography is a fun one. I'm gonna see if there's yeah, so there's different types of anion of exchange columns, right? It's either very positive or very negative. And the idea is that you want to have the protein stick to the resin. And this basically tells you about the charge of the protein at any given pH. Yeah, I'll cover this more when we get so yeah. So the one thing you should know is that for anion exchange columns, we have a stationary phase that is positively charged, and we're trying to exchange a negative test charge for a negatively charged protein. For cation exchange, it's the opposite. We start with a negatively charged resin and we're trying to exchange positively charged proteins. Here's an example, right? So this would be a an anion exchange column, right? So I say it's anion exchange column, right? Because we're initially binding charged ions and we're performing an anion exchange. And you'll see that at the bottom here, right? So look, so here we have, right? We have this, right? So we put this sodium chloride in here, right? What's going to happen is because we put a bunch of positive charges in here, the sodium is just going to go straight through, and the chloride is going to get stuck here, right? If you look down here, see how this chloride is stuck, right, on these beads, right? And how these sodiums have been left out, right? So the chlorine ions get stuck, right? Chloride. And the anions will flow straight through. Now, if we add our, like, a solution of proteins, right, at a certain pH, what we would expect to see is that the negatively charged proteins will actually replace the chlorides. And the positive ones will just go straight through again, right, and go to waste, right? This charge of the protein is determined by the pH you set it at, right? Based on the pI, right? Remember, if pH is below pI, you have a positive charge, and if pH is above pI, we have a negative charge, right? So if I have a protein that has a pI of 6, you can imagine that if I was at pH of 2 for my exchange column, right, I would probably want something that is an a cation exchange column, right? Because my protein is going to be positive, right, at pH 0 or pH 2 with a pI of 6. And on the other hand, if I was at pH of like 10, right, I'd want an anion exchange column, right, because my protein is probably going to be negatively charged, right? So just keep that in mind. And here you can see, right, what's going on here. Yep. Charged compounds adsorb to resin having the opposite charge. Yep, there you go. Yeah, this positive is kind of just sitting up there, right? And you can notice here that, if you put more in, right, basically these will get stuck, right? And these will try to elute out faster, right? Because, and like, they will try and get attracted to these chlorides down here, but there's so much negative charge, like plus charge around here, right? That they're going to be pushed down and out because the like charges repel, right? Like I said before, negative ones will stick. And these charged proteins will knock off these chloride ions. And then, like I said before, positive charge flows straight through the ion, the column, right? Yeah, this is just the idea that, like, it depends on what, like, the analysis depends on what type of protein you're looking at, right? So if the protein of interest was positively charged, right, they would be present in the first, like, round of liquid, so in this round of liquid, right? But once you elute out this section here, there's it's possible that if your protein is negatively charged, they'd be in the second round of elution, right? So the first round of elution, right, has these positive charges with the chlorides. The second round of elution has these negative charges, right? Like I said before, right? Same thing here. If protein of interest, yeah. So if it was positively charged, right, present in the flow through, right. If it was negatively charged, right, you would begin adding very high concentrations of sodium chloride, right, and this would cause the chloride. Do they have? Yeah. This would basically cause, right, the chloride to start bumping up against these negative charges and pushing out the negative charge, basically replacing them, right? Like a probability game, right? If you have more of a thing, right, the probability of that thing bumping something else out of the way is much higher, right? Here you can see, right, see what's happening, right? You put these chlorides in and see how these charges are now moving, right? See, look at that. See, right? So like now the chloride, right, has replaced all of these negatively charged proteins, right? It's still kept, the very strongly charged ones have stayed in there, but if you add enough, right, even those will also get eluted out, right? The point here, right, is that if you look here, right, if you need to add more sodium chloride to get these purple ones to flow out, right? So, right, see how much we've added here. Look at how much we've added here compared to how much we have here, right? So adding more of the sodium chloride, right, has allowed us to elute out more of these proteins, right? So now we're able to see which ones are more negative and how the pH affects them, right? The rest of it is not that important. Again, this whole thing of absorbance at 280, just remember that for 280 nanometer absorbance, you're looking for tyrosines and tryptophans, not phenylalanines. Phenylalanines have resonance, right? So resonance is what absorbs them, right? That's why tyrosine and tryptophan absorb 280, because they have a lot of resonance structures, right? But phenylalanine, while it does have resonance, doesn't have as much as tyrosine and tryptophan. Affinity chromatography, this is just about ligands. Um, you're basically using a resin, right, that has a chemical group, right, a ligand on it, right, and then you want to see if that protein, the protein that you're looking at, actually binds the ligand, right? So you're basically going to fill, instead of filling the column up with like ions, right, you fill the column up with this ligand, right, and then you dump your protein in there, or you dump like a solution of like, you dump this like solution in, right, and then you take different elutant value, like elutant liquid samples, right, to try and figure out, does the protein bind or not. So if your protein has no affinity for the ligand you put in, it'll just flow straight through the column. However, if the protein does have affinity for it, once you use a like another competitive agent to kick out the protein from the bound ligand, you can elute the protein. You can elute the protein out. Like here's the bound protein is eluted off and collected, right? And you can elute out the protein, right? And that basically confirms that protein binds to that ligand, right? And right, so this affinity chromatography does depend on specificity, right? So enzymes generally bind very specific things, right? So you have to be very specific with the type of ligand you use, right? If you don't use the right ligand, it probably won't bind, right? If you take Biochem 426, the lab, you'll end up using something like this, imidazole, with a nickel. I think it was a nickel tab for us, right? It was really interesting. So yeah, you can engineer these, yes, like affinity tags, right? So for example, in Biochem 426, you add a 6x histidine tag to your protein, right? And what that does is, that's not a ligand, however, it's like an add-on, right? And then what you do is that you put nickel in your column, right? So you basically have a column. I'm trying to draw this here. You have this column, right? And this has a bunch of nickel in it. I'm just going to do Ni, right? Nickel, 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 right? And this 6x histidine tag gets put in here and gets stuck to the nickel, right? And then anything else just flows straight through, right? But the proteins with this tag on it get stuck in this column, and then you can elute it out and then do analysis on it later, right? Here we've got SDS page. This is probably one of the more important ones that you'll see in this class. You can learn a lot from SDS page. You don't really have to know about how SDS page works, really. There's a positive terminal and negative terminal, and basically proteins travel depending on their charge. And if you apply certain things to it, you can get certain traveling paths and all that stuff. But you can learn about the purity, the size, and the number of subunits. If you use beta mercaptan, a reducing agent. There are cases, right, where you don't need a reducing agent, right? Sometimes there isn't any covalent bonds to be reduced, cis disulfide bonds to be reduced, right? So not always the case that you always need reducing agents, but generally speaking, they like to test you on that, and they do like to throw in like a reducing agent, resulting in like a multi-subunit complex being broken apart. So just be aware of that. Sodium dodecyl sulfate. This is just a thing that, one, denatures proteins, and two, coats them in a negative charge so that they move from the negative terminal to the positive terminal, right? If you don't put this coat on, the proteins just kind of travel wherever, right, based off of their pI, right? So depending on the pI and the pH that you put them in, right, they'll travel in the direction that suits their charge. But that's only if you don't apply SDS. If you do apply SDS, they'll always go this way. Right? The rest of this is not super important. Right, so SDS page runs under denaturing conditions. Native page is if you don't have SDS, right? It's just native, right? Right, so sodium dodecyl sulfate, right? It's a denaturant. It coats proteins with a negative charge. I would memorize these two. This is also something to keep in mind. Just keep in mind that boiling a protein breaks it, right? That seems to make intuitive sense, right? If you heat something up a lot, right, it'll eventually break apart, and that's basically what this is saying, right? It unfolds, right, and it breaks apart the protein. It doesn't break the bonds, but it does unfold the protein and break up the primary, not the primary structure, the quaternary tertiary structure, right? But yeah, this right here is for denaturing, and this right here is for reducing disulfide bonds. And yep, see, like I said before, if it's coated with SDS, it migrates only based on molecular weight. If it's not SDS coated, it migrates based on weight and charge, right? And the reason it does that is because it's got a uniform mass to charge ratio when you apply SDS. Yeah, so here if you look at this, right? Notice here when you have beta-mercaptoethanol, right? The protein size is like 36,000 or something, maybe 33,000, right? And if you don't have beta-mercaptoethanol here, it's around 66,000. So what that tells me is, right, you can't just have mass disappear, right? So you have 33,000 here and 66,000 here. That must mean you have two subunits of 33,000, right? And they are held together by a covalent disulfide bond, right? I hope that makes sense, right? The idea is that because we have beta-mercaptoethanol here, a reducing agent, and we have a 33K subunit, right? And we don't have beta-mercaptoethanol here, and we have a 66K subunit, that tells us that this reducing agent is reducing a disulfide bond, right? And there are two 33,000 subunits in this band right here that add up to make this 66,000 protein. Right. Yeah, Kumasi staining, you do this in 426 again. I wouldn't be too bothered about this, really. Not for this class. You basically use it to actually see what you're looking at. So, yeah. I wouldn't be too worried about this. And yeah, the idea here is that you can couple multiple techniques together. So often they'll like give you like multiple different experimental pieces of experimental data, and you got to figure out how things work from that. But other than that, I don't think there's really much else to go over on this lecture. Might have been a little bit fast, but hopefully I got like the main points down. There was a lot of slides in here, but I don't think they were all necessary. So you should be able to get by with just what I've talked about here. And hopefully if that makes sense, great. If it doesn't, hopefully it'll make sense after you take a look at some problems or you try and work through it yourself a little bit. But if you don't understand something, feel free to come find me in the IC if I'm still there. And in the future, you can always ask one of the instructors, right? Gordon and Scott Clary if they're still there, right? So go ahead and feel free to do that, and hopefully the video helps. But yeah, on to the next one. Thanks. Bye bye, guys.